Hello, I'm Aishat Alagunju, a master student at Western University under the supervision of Professor David Jeffrey.
I am David Jeffrey from the University of Western Ontario. Pythagorean triples, quadruples, and beyond. We start off by reviewing the non-properties of Pythagorean triples. Definition: 3 integers, a squared plus b squared equals c squared. And well-known examples are 3 squared plus 4 squared is 5 squared, 5 squared plus 12 squared is 13 squared, 6 squared plus 8 squared is 10 squared. These have been known for over 4,000 years. On the screen you see a picture of a Babylonian clay tablet approximately 4,000 years old, and on the tablet are cuneiform marks which have been interpreted as being a list of Pythagorean triples. That shows you how old Pythagorean triples are. One of the first questions to ask, of course, is how do you generate Pythagorean triples? And these methods, like the numbers, span 4,000 years. The first method we have for generating Pythagorean triples is a set of parametric generators which are found in Euclid's Elements. A equals m squared minus n squared, b equals 2mn, c equals m squared plus n. When m and n are given integer values, they generate a Pythagorean triple ABC. Leonardo of Pisa, popularly known as Fibonacci, lived in the 13th century. In addition to introducing Arabic numerals into Europe, he also wrote a book called the Book of Squares, in which he included a method for generating Pythagorean triples. The method used 2 sequences. The first sequence is just the odd integers, and the second one are the odd integers which are also squares. The method proceeded by choosing a square from the second sequence, and then finding its location in the first sequence, and then adding up all of the elements in the first sequence up to and including the chosen number. And I have illustrated this in a Maple worksheet. So this Maple worksheet starts off with a sequence of odd integers. That's the first sequence that Fibonacci uses. We notice that the sum of odd integers is a square. And then we have a second sequence, which I've written here, which is the squares of odd integers. Fibonacci's method starts by selecting an element of the second sequence. Let's say 25. Take the square root of that is 5. The index, and then j is the index. It'll be 3 into this sequence. So that's the value of j. We can use that to refer to the 25. Now we find the location of 25 in the first sequence. If we look up here, we see it is the 13th element of the first sequence. And we can express k, its position in the first sequence, as a function of its position in the second sequence, which is j. We now add up all the elements up to, but not including 25, and that will be our value of b, also expressed in terms of j, the position in the second sequence from which we started. And then finally, we add up all of the elements including 25, and that gives us c. Here is our triple of 2j minus 1, etc., etc., where j, as we remember, is the position of the selected square in the second sequence. And then I have printed out a sequence here from 2 to 5. We recognize 3, 4, 5, 5, 12, 13, 7, 24, 25, 9, 40, 41. We return to our main presentation. I comment here, Fibonacci's method does not find all triples. In particular, once you have chosen the first element, you are locked into a particular triple. So for example, there are 2 triples that start with 15, and Fibonacci's method clearly will only get one of them. Moving on from the 13th century to the 18th century, we come to Euler. Euler liked to use trigonometric functions rather than polynomials. in his investigation of Pythagorean triples and similar quantities. A particular interpretation of that is that since sine squared plus cos squared equals 1, if we take a Pythagorean triple and divide by c, we clearly see a connection between sine squared theta and a over c squared. And then here is a little geometrical diagram connecting theta. And in particular, if we look at the tangent of theta over 2, we see that that is m over n, where m and n are the parameters that were used by Euclid to generate Pythagorean triples.
A recent method of generating Pythagorean triples is the use of ternary trees, which occurred in the past 10 years or so. A ternary tree is a tree data structure in which each node has at most 3 child nodes. In other words, a tree with at most 3 branches. A Pythagorean triple ternary tree is a structure of all primitive Pythagorean triples. Each has 3 children. Famous examples of such methods are the 3 Pythagorean matrices and the 3 prize matrices. It involves the generation of 3 sets of triples from a single set of triples, ABC, with A being hard, using matrix multiplication with either Pythagorean matrices or prize matrices. Looking at the 3 Pythagorean matrices B1, B2, and B3, and the 3 prize matrices P1, P2, and P3, using the famous Pythagorean triple 3, 4, 5 as our example. If we multiply 3, 4, 5 with the first Pythagorean matrix, we have 15, 8, 17. Multiplication with the second Pythagorean matrix gives you 21, 20, 29. And the matrix multiplication with the third matrix gives 5, 12, 13. A visual representation of the tree gives 3, 4, 5 using Pythagorean matrices, and you have 15, 8, 17, 21, 20, 29, and 5, 12, 13. If you take 15, 8, 17 as a new tree, as a new generator of the new set of Pythagorean triples, you have 13, 12, 37, 6, 72, 97, 33, 56, 65. Likewise, if you use 21, 20, 29 as the new generator of Pythagorean triples, you have 77, 36, 85, 119, 120, and 169. And lastly, 5, 12, 13 gives you 45, 28, 53, 55, 48, 73, and 7, 24, 25. The same way, if you choose any of the resulting triple and you apply matrix multiplication with either Pythagorean or price matrix, gives you another 3 branches, and etc.
A final comment on methods of generating Pythagorean triples is a paper by Frisch and Wasserstein. They point out that Euclid's method, m squared minus n squared 2mn, m squared plus n squared, will always start with an odd number, and then the second element of the triple will always be an even number. And they ask, well, what happens if you want the other way round? What if you want to start with an even number and then go an odd number? So in addition to 3, 4, 5, how do you generate 4, 3, 5? Well, the obvious answer would be, well, we just reverse the order of the polynomial formula. So we just write 2mn, m squared minus n squared, m squared plus n squared. And they say, well, that is 2 separate methods of generating Pythagorean triples. Does there exist a single method based on a polynomial parameterization that would get not only 3, 4, 5, but also 4, 3, 5? And the answer to that is yes. Here is their polynomial parameterization of all possible Pythagorean triples whether starting with an even number or an odd number. Leaving behind the generation of triples, there are other things you can do with Pythagorean triples other than generate them, to count them or to plot them. However, it turns out that in order to count or to plot, you have to bring into consideration the ordering of the triples. So you make a list of the triples, but exactly in what order do they appear? And there are several possibilities here. For example, you could take the last element of the triple, the one that sort of measures its size in a sense, and order by that. Or you could order by the first element. And then inside each triple, you could either have them always starting with the odd number or always starting with the even number, or you could always rearrange them so that they were in ascending order. Sometimes the triple would start with an even number, sometimes it would start with an odd number. And those different orderings influence what you see. With that in mind, we're going to plot triples. And the way we're going to do it is we're going to take the first two elements, A and B, and treat them as the coordinates of a point. And depending upon how we order the triples, we will get different looking diagrams. For a start, let's suppose we always start with even numbers. Then this is the plot we get. And looking at it, you can see that the dots line up on inviting curves in the plane, which you'd like to describe. And we go into that in the paper that accompanies this talk. Now, if on the other hand, I order the triples so that they are always in ascending order, so the first element is always the smallest and the second one is the largest, our diagram looks rather different. Because, of course, the y-coordinate will always have to be larger than the x-coordinate. And so we get this whole empty quadrant here, and all of the numbers jammed up into this roughly triangular shape here. Notice again, we get these inviting curves. That's all we're going to say about triples. Let's move along to quadruples. So what is a quadruple? Well, it is A, B, C, D, where a squared plus b squared plus c squared equals d squared. A few well-known examples are 1 squared plus 2 squared plus 2 squared is 3 squared, 2 squared plus 4 squared is 6 squared, and 3 squared plus 4 squared plus 12 squared is 13 squared. Several people have discovered parametric generators for Pythagorean quadruples. Here is one such one here. You notice that in order to generate quadruples, we need 4 parameters, whereas for triples we needed only 2 parameters. In addition to this all-inclusive one, a rather fun way to talk about generation of quadruples is to say, let's take triples and chain them together. So in particular, we start with the triple 5, 12, 13. And then we search and we see there is another triple that starts 13, 84, 85. So now we join those two together and we end up with 5, 12 makes 13. 5 squared plus 12 squared makes 13 squared, which now takes the place of the 13 squared in 13 squared plus 84 squared. And so we end up with the quadruple 5, 12, 84, 85. A rather different take on quadruples was Euler in 1771. He described a number of 4x4 square arrays, some of which were magic squares, and some of which were magic squares of squares. So, in other words, you start off with a 4x4 array of numbers, then you square every element in the array, and that becomes a magic square. Here was his parametric description of such a 4x4 array. He presented this as a table. He didn't have the language of matrices in that day, so we have also written it as a table, reproducing the way it looked in his original paper. If we take a numerical example, this is taken from Euler's original paper, he substituted these values for the 8 parameters, and he obtains this array here. After you square each element, you end up with this array here. I like the fact that there's a 1 and a 1 in spite of all these other large numbers around. And I'll leave it to you to add up the rows and the columns and the diagonals, and each of them adds up to 16,900. The matrix he started from actually has some other interesting properties. Namely, each of the columns and each of the rows is orthogonal to the other rows and columns. So if you take this matrix and then calculate the transpose times the matrix, or the matrix times the transpose, you will obtain a diagonal matrix with a constant down the diagonal. And then we move on to higher dimensions. It turns out that you can make Pythagorean n-tuples of any size. One entertaining example is to take the idea of chaining together more elementary tuples into an infinite array. We proceed as follows. 1, 2, 2, 1 squared plus 2 squared plus 2 squared is 3 squared, so that's 3. 3, 2 times 3, 2 times 3 is the quadruple 1, 2, 2, simply multiplied by 3. And then we have all of these together make 3 squared. And now we have 3 squared, 2 3 squared, 2 3 squared, and so on. A second interesting thing you can do is to count the number of n-tuples in any given interval. So as I said, the question is, how do you order n-tuples? Let's order them by the last element, which is probably the best measure of size. If we do that, then we can ask, fixing the size, so here we're going to fix the length or size of the n-tuple to be the size of the last element, and we're going to fix that to be 20. So our question is, how many n-tuples are there in which the last element is 20 or less? So with dimension 3, there are only 3 triples whose sizes are less than 20. When you go to dimension 4, that's a quadruple. Then you end up with 14. And then, as you see, as you add dimensions, it becomes easier and easier to find appropriate n-tuples which are of size less than 20. And that continues up until dimension 8. And then from dimension 9 onwards, that number of possible n-tuples will decrease because, trivially, we expect that by the time you get to dimension 20, it will be impossible to get any 20 tuple which has a length less than 20. Thank you.